Good day, guys, and welcome back to the Diverse Node Mobility Front End program. Today, we will discuss the Module 6, and this would be the fifth session. All right, so I'm going to share my screen to you. Okay, so here, in the Module 6, we will discuss functions. In this module, you will learn about function, how to declare, define, and invoke functions, the scope of variables, local variables, and function parameters. We will also discuss pointers, arrays, structures as functions, parameters. Also function result and the return statement. Void as parameter, pointer, and the result. And also parameterizing the main function and also external functions and the external declarator. Lastly, we will also tackle about header files and their roles. All right, so functions, why do we need them? Okay, so let's talk about the functions rationale. We have come across functions many times so far, but our view on their merits have been rather one-sided. We have only invoked the functions by using them as tools to make our life easier and to simplify time-consuming and tedious tasks. When we want when we wanted to copy a string, we use strcpy. When we wanted to emit the value of a variable, we use the printf functions and etc. When using functions in this way, we have to remember to include the proper header with a #include directive. You already know that the compiler needs to be told what functions you're going to use. The complete executable file is created as an assembly of your code, referring to other functions and the code of these functions. Now you are going to learn how to declare and write your own functions and how to use them. We will also tell you how to use functions written by someone else, even when we don't have their source code. You will learn how to publish your functions with other developers and how they are shared. We will write several functions together, from the very simple to the more complex, which will require your focus and attention. Why would we want to write functions? Okay, so here's the reason number one. If often happens that a particular piece of code is repeated many times in your program, it is repeated either literally or only with some minor modifications consisting of the use of other variables in the same algorithm. It also happens that the programmer cannot resist simplifying their work and begins to clone these pieces of code using the clipboard and copy-paste operations. Now imagine there was an error in the original piece of code. The programmer copied. The programmer now has to go back through all the parts that she or he and correct every single one. How frustrating would that be? There is also a high risk of the corrections causing the other errors. Murphy's law is ruthless. We can define the first condition, which can help you decide when to start writing your own function. If a particular fragment of the code begins to appear in more than one place, consider the possibility of isolating it in the form of a function invoked from the points where the original code was placed before. Alright, so here's the reason number two. It may happen that the algorithm you are going to implement is so complex that the main function begins to grow in an uncontrolled manner, and suddenly you notice that you are having problems simply navigating through it. You can try to cope with this issue by commenting the code extensively, but soon you will find that it dramatically worsens your situation. A lot of comments makes the code larger and harder to read. Some say that a well-written function should be viewed entirely at one glance. A good attentive developer divides the code into well-isolated pieces and encodes each of them in the form of a function. This considerably simplifies the work on the program because each piece of code could be encoded separately and tested separately. This process is often called decomposition. We can now state the second condition if a piece of code becomes so large that reading and understanding it may cause a problem. Consider dividing it into separate, smaller problems and implement each of them in the form of a separate function. This decomposition continues until you get a of set of short functions easy to understand and to test. Okay, so let's have version number 3. It often happens that the problem is so large and complex that it cannot be assigned to a single developer and a team of developers have to work on it. The problem has to split between several developers in a way that ensures their efficient and seamless cooperation. It seems inconceivable that more than one programmer should work on the same piece of code at the same time, so the job has to be dispersed among all the team members. This kind of decomposition has different purpose to the one we described previously. It's not only about sharing the work, but also about sharing the responsibility among many developers. Each of them writes a clearly defined and clearly described set of functions, which, when combined, will give the final product. This leads us directly to the third condition. If you're going to divide a work among multiple programmers, decompose the problem to allow the product to be implemented as a set of separately written functions. Alright, so what does the compiler need? What does the compiler need to know in order to invoke a function? If the compiler is analyzing your program and encounters something that looks like a function invocation, for example, in this context, number of sheep equals count sheep parentheses. It will try to make sure that the function you want to call is available. The parameters you've specified are consistent with what is expected for the function. The return type of the function is compatible with the type of targeting L value. In other words, compiler must have the following information for each functions you're going to use. What is the name of the function? How many parameters does the function expect and of which types? And what is the function's return type? If you don't provide this information, the compiler will try to deduce it from the first invocation that appears in your code that is called an implicit declaration of the function and is both convenient and dangerous at the same time. Imagine what havoc can be wreaked if the first function invocation contains an error. The compiler can derive information about the functions from two sources. First, the declaration of the function. Second, the definition of the function. Okay, let's have the declaration versus definition. The declaration of the function is the part of the code containing all three pieces of information, which are name, parameters, and type, but doesn't contain the body of the function. In other words, it says how to invoke the function, but says nothing about what this function does and how it does it. We can say the declaration gives complete information about the function interface, but there's nothing about the implementation itself. The declaration of the function is often called function prototype. A definition of function is a part of code containing its full implementation, including the body. So here's the example of declaration, and the second statement is an example of definition. Okay, let's have our first function. Let us start with a simple function. Its sole purpose to signal that it has been invoked. The function won't have any parameters, won't return any result, and will named hello. So here's its definition. So here is the function called hello, and we have print you've invoked me with fun and return. So this simple function, its purpose is to signal that has been invoked, and we don't have any parameters here, so we add void and won't return any result. So the result is only this printf. Right, so what does the definition contain? The first void means that the function does not return any useful value. A type name may appear at this point, announcing that the function calculates the result of a given type and returns it after completion. An opening parenthesis, in fact, the presence of the parenthesis assures the compiler that it's dealing with the definition or declaration of the function. A parameter list, or the word void, if the function doesn't expect any parameters. A closing parenthesis, and a complete block enclosed in curly brackets and containing a set of C language instructions and declarations. So how to how do we invoke our function? We can invoke our new function in the following way. So here, hello, and then open and close parenthesis. Then don't forget the semicolon. How do we not invoke our function? We must not invoke our function in the following way. We try to treat it as if it evaluates and returns the value of type int, which is at odds with the declaration. The compiler will emit an error message. Invoking it is like this is prohibited too. So having a value inside a parenthesis is prohibited. We are trying to pass an argument whose type is int through the declaration's void parameter. Right, so let's have function eventually invoked. In the editor is a complete program, ready to compile and run, including both the function definitions and its invocation. Note that the place in the code where the invocation of the hello function has appeared, and the compiler is ready to invoke the function there. It knows that the function's name, it knows that no parameter it expected, and it knows that no return value has been provided. Imagine that due to some important reason, we had to change our code. It looks like this. So here is the example. Okay, so here int main void print, then we are about to invoke hello, then we have hello function, and then we return your from hello, and here's the hello function. You've invoked me, what a fun. So a layout of our code like this will puzzle the compiler because it forced to guess all the traits of the hello function before the compiler even reads its declaration or definition. You should expect the compiler to generate a warning message and implicit declaration will perform its deduction. The deduction is very simple. It assumes that all entities of unknown types are ints. This means that the compiler is convinced that the actual hello declaration looks as follows. So we have int and the name of our function, and we will have void inside the parentheses. The mismatch between the implicit and explicit declaration will cause the compiler to signal a warning or an error. Don't forget, whenever the compiler knows that the entity has been declared but knows nothing about the entity's it thinks it's an int type. What should we do to convince the compiler that the implicit declaration is not a good idea? Is there even anything we can do? Yes, there is. We should warn the compiler that the function will be used and provide complete information about it. In other words, we ought to provide a declaration before the first invocation occurs. Look at the editor. There's correct unambiguous code. So here we have declared the void, the hello function before we run them or execute it or um, state or call the function of hello, right? So that is how we do correctly the implicit declaration. Okay, so how about the return statement? The return statement executed inside any function causes immediate function termination and a return to the invoker. The form of the return statement and whether there is a need to use it depends on the following circumstances. If the function is defined as void, then the acceptable return statement looks like this: return, then semicolon. If the body does not contain a return statement, it will be implicitly added after the last instruction of the function's block. This means that you can write the hello function in the following way too. So here, void, then we have hello, the parameter would be void or not. Void, and we have the printf, you remove what font. Okay, note that more than one return statement may exist in the function body. If the function type is not specified as void, the only acceptable form of the return statement is as follows: return and then the expression, where the expression must provide the value of the type matching the type of the function. In this case, using the return statement is mandatory and you cannot omit it in the function body. If the body does not contain a return statement, it will be implicitly added after the last instruction of the function's block. All right, so how about the functions and their local variables? Function blocks and blocks in general can contain variable declarations, as many as you need. Now it's time to show you a very important rule underlying the whole complex issue of ranges. The rule reads as follows: the blocks are opaque to the declaration contained therein. This means that if we declared a variable inside a block, the variable will be known and recognized inside the block and consistently will be known in the other part of the program. This also means that the name will not interfere with other variable with identical names defined inside the block. So here's the user defined and here's the system defined. So we have the local variable and we have the global variable. The difference between local and global variable is that the local variable is only known in the specific block, and while the global variable can be known, uh, for example, you are having many function in your code. For example, you have three function. The first function is main, and then we have hello function, and the next one is hi function. So the variable, for example, variable I is known in all of the function. So that is the difference between global and local variable. So let's have a look at the example in the editor which illustrate this rule. We want the hello function to be more exciting and print its happy message twice. We will use the for loop for this task. We will also need a control variable, so we add the int I declaration at the beginning of the block here. The I variable is recognized only inside the hello block. Here's the hello block and nowhere else. Okay, so if you need to have another variable of the same name, but inside the main function, you can declare it without any problem. So we can declare it again. All right. So each of the function have their own I variable. The variable exists independently of each other and have nothing in common. Okay, so that is example of local and global variable. So we can declare it twice in different function. All right, so now let's understand the global variable. It should help you understand the operation of both kind of variables. This is how it works. The program begins with a declaration of global variable. This one. It's truly global because it's outside of any function, like function fun and main function. This implies that the variable is accessible to all functions declared in the source file. The local variable which declared within the fun function is known only in the function and has nothing to do the variable of the same name declared inside the main function. So since global is declared outside any functions, just like fun and main function, it is truly global. And however, we can find variable local inside only the fun. This local is only accessible to fun function, and this global is declared outside. So this is truly global. All right. So even though we are using the global variable global, which is outside of the blocks, if you code like below, you may experience some problems because it may be used in the fun function because it's before it's declared. Remember that a function or variable must be declared before it's used. We can expect the following text to be sent in the screen. So I'm going to print this one. Run this one. So here's the expected output. Main local 1. So global 1, local 2, and global 2, local 1, and global 3. Okay, so that would be the expected outcome of this code. All right, so let's have the function parameters. The function parameter is a special kind of local variable. It behaves like a local variable. Its name is not known outside the function. However, it differs from the local variable in two important features. So first, the parameter is not declared within the function. It is not part of the function definition, but must be declared inside a pair of parentheses after the function name, which means that the parameter declaration is a part of function declaration. Look at the following function declaration. So here's the function. The function's name is hello2. So its function parameter is inside the parentheses, and we have its data type and the name of the parameter. So the times variable may be used inside the function in exactly the same way as if it were a local variable. This is called a formal parameter. Secondly, a prototype of the function containing formal parameters forces us to invoke the function with a list of expressions, and the number of expression must be equal to the number of the formal parameters in the prototype. The types of this expression must be compatible with the types of the corresponding formal parameters. Each of these expressions is called an actual parameter. Okay. And lastly, at the beginning of the invocation, every formal parameter is assigned the value of the corresponding actual parameter. So these are the things you need to know about function parameters. So let's look again at the hello2 definition. It clearly shows that these three invocations are valid. They are delivered a value of type int to the formal parameter. So here's the definition, hello2. Then we have 100 inside the parameter. So here, as you can see, the actual parameter is a literal. Okay, so let's have this one. The hello2 definition, another definition, not too many. So the actual parameter is a variable. All right. So how about the third one, the function definition? The actual parameter is an expression. So this is an expression. So these are the different definition of a function. So the first one is an actual parameter. Next one is a variable since it is declared. Okay, so how about this one? If you are saying an operator, so that is an expression. We cannot call the function hello2 in any of the following ways. So here, hello2, then parenthesis, and then semicolon. So the comment for this function is too few actual parameters. And this one, hello2 1, comma 2. And then we can say too many actual parameters. And for the third one, this is an incompatible actual parameter. So take note of this. So the first one, we don't have any parameters. So this is few actual parameters, too few. And this one is too many. This one, the last one is incompatible. Since this is a string, right? Okay, so the values of actual parameters are assigned to formal parameters at the beginning of the function execution. Let us assume that the hello3 function has the following declaration. Okay, let's have function hello3, void hello3, then int I float f. That has been invoked as follows: hello3, 100, and then 3.14. The following assignments will be performed implicitly and beyond our control. F is equals to 3.14. The second formal parameter is assigned with the current value of the second actual parameter. The parameterized function may modify its own behavior according to the parameter's value. Look at the updated hello2 function provided in the editor. If you invoke this function as follows, hello2 and then 100, the following assignment will take place as times is equals to 100. This causes the function to manifest its joy 100 times. Let's have the function results. If the function has been declared with a type before its name, it must be performed the return statement equipped with an expression. We will write we will write a simple program helping us to solve a trigonometry problem for right-angled triangles. The program will calculate the length of hypotenuse using the lengths of the legs. This is what we need to do. First, ask the user for the length in the first leg and square it. Then next, ask the user for the length in the second leg and square it. And lastly, square the sum of both values using the sqrt a parenthesis function, and pay attention that the math.h header file needs to be included at the top of our source. You can see the first version of the solution in the editor. So as you can see, all we need to do is ask the user, this one, ask the user to the length of the first leg and square it. So in order to square it, we are going to declare the square of the a. So we rename it the variable as a underscore sqr, and for the solution of this is a times a, and we will also prompt the user or ask the user to enter the length of the second leg, and we are going to square it, and then we are going to square using the square this one and this keyword, and don't forget to add the hash include mod.h, and then after that we are going to sum, and then it will give us the result, and the variable for that is c that has been declared as a float. So how about introducing a function? In the previous code, there is a repeated clause used to square a leg. It's the perfect opportunity to introduce a function into our program. The function won't be particularly advanced we expect it to. So the first one is accept one parameter of type float, square the value of the parameter and return it as the result. The result type is float, and the next one we will name our function square. It's a good practice to name functions using verbs. So here's our first version of our function. So we have declared the float here, that the parameter of our type is a float, this one, and we rename our function as square. Okay, so the result type would be float, this one. All right, so of course the function could be slightly simplified. Here it is. So instead of writing this code, you can write it this one. So float square float, then parameter, and then return param times param. Okay. All right, so can you explain the difference of the first version and the second version? Okay, so the difference between that one is we don't um we don't declare the x underscore sqr in the in the second variable in the second expression. So as you can see, they have the same function on how it was written, but on the block's body they have different, and the second one is simplified. Okay, so the first thing that you are going to see is you see or notice that return is declared here first. And since we don't need to use xqry, you are going to put the expression after the return, or put the equation after the return. So it is param times param. So we don't use the x underscore sqr in the second snippet. So that is the how to simplify the first version of the function. So now we are going to use a program that we have. Let us use the function in the program. Here it is. So we have used the square function, and we have the main function. So in the square function, just like we have did earlier, that it was simplified, it returned to param times param. Okay, so let's have the main function. We have declared a, b, a square, b square, and c variables here, and the data type is float. And we are going to prompt the user to enter what is the value of a, and we also okay, can you find where did we get the square keyword here? Okay, so square keyword was declared in the first function. Okay, so we called uh instead of using an equation here, a times a, since square was declared param times parameter, so this is the main function. So we called the function as a variable here. And we all know that square function has its function parameter times parameter. Okay, so that is how we use the first function, which is square, to the main function. All right, so we can make one simple modification. Note that the s and a sqr. Note that a sqr and b sqr use as a temporary containers only. The C variable is utilized in the same way. We can remove them and take a look at the editor. So as you can see, where is this a square and b square? So it was not declared here, but we can see that a sqr and b sqr in this code was removed. So this code remind us that we can add the formula or the equation after the printf, or we can declare it inside the printf. So our code has become shorter and clearer. Okay, so let's have the function parameters that are scalars. We already know that actual parameters values are assigned formal parameters during function invocation, which means that executing the program in the editor will send the following text in the screen. So here's the expected output. I receive value 1000, I receive value 111, I receive value 1111. So if I'm going to run this one, okay, so we will get the expected output. So how did we get that output? So how do we get that result? So first, as you can see, um, in the void function, in the function, the parameter is to print I've received value and then the integer. So the first is function and it is a literal. So as you can see, we have declared, oh, in the output you can see that I've received the value 1000. So that's how we get that. And then a new line. So in the second line we can see the variable. So what's the variable? So in the main function, the variable was declared its value and it is 1111. So that is how we get the second line. And how about the third line? I've received the value of 1111. So the variable, which is 1111 plus 1000. So that is how we get the 1111, the third line. So this reminds us that these functions have a different parameters. The first one is literal. Next, the second one is a variable, and the third one is the expression. So what happens if the function changes the value of the formal parameters or parameter? It is always possible. In other words, what will the program in the editor send to the screen? The function not always prints its only parameter, but modifies increments it. Does this mean that the function modifies not only the parameter, but thereby also the value of the variable? Not at all. The program will emit the following text. I've received the value 111 and the variable 1111. Variable equals 1111. So as you can see in the program in the code in the editor, so as I run this code, you can see that I've received a value of 111 and variable 111. So as you can see, the difference between that one is we don't have the equal sign because it was not declared here in the printf. So if I'm going to add equal sign, so we will have the same result. Okay, so first one is when do we get that I've received value of 111? So as you can see, we have declared the name function here in the first one. And in the function, you can see that it was declared to print I've received value in this one. And we have the %d, which is talks about the variable, which is int variable, and the name of the variable is variable, and the value and its value is 1111. So that is how we get I've received value of 111. And how about the second line, variable equals 111? So this is simply a printf function on which we declared some string here and call the variable value. Okay. Okay, so this observation leads to the following conclusion. Function is not able to change the actual parameters value. The actual parameters value is copy. In the formal parameter and the relationship between them definitely ends at this point. Any change in the formal parameter does not affect the state of the actual parameter. The actual parameter and the formal parameter are two entirely separate entities, and the only contact between them occurs when the function is being invoked. From that moment, the two parameters live their own separate lives and do not interact in any way. This kind of cooperation between parameters is known as by-value parameter passing. However, we can deal with this limitation using pointers. This is how the scanf function works when it has to get the value from the user and assign it to a variable. Let us take a look at the program. Okay, so if I'm going to run this program, we will get this output. I is equals to 100 and I is equals to 200. So first, on the first line, we as you can see, I is equals to 100. We get that answer because it was written simply in printf function, and this is I is equals to percent %d, which is the integer, and the integer value of I is equals to 100. So that is how we get that line. How about the second line? I is equals to 200. So as you can see, in the second printf function, we notice that we have declared the function x, and then we have declared p here. So the pointer p, which is declared here, the pointer p, the function of that is was written on the function x here, on the function x. Okay, so the pointer, which is the variable I, is equals to 100, and its expression added another 100. So that is how we get the 200. So let us navigate through our program. First, we declare the I variable and initialize it with a value of 100. We declare the P and initialize with a pointer to the I variable. And the figure below illustrate the current figure configuration. So we also invoke the function x and passed the value of p to it. This is the function x, and pass the value of p to it here. The value is copied to the PDR parameter. The figure illustrates the resulting configuration. So that is how we describe into illustration this expressions. Also, in the function x exits, the p variable has not changed its value. Because the rule we defined several slides ago is respected without exceptions. The I variable has changed its values. The value it's now is 200. The output screen looks as follows. This one, as we discussed earlier. This, despite the fact that we cannot change the actual parameter value at all, we have successfully changed the variable value by using the pointer, which remains unchanged. We cannot we cannot simplify the main function using the following way. We can. All right. So just like we have did earlier, we can use this one. So print and then I, and then so literally we are going to get the first line I is equals to 100. So another one, we have function x and I. So function, here's the print function, I is equals to percent %d and then I. So we will have the another 100. So the pointer p is completely unnecessary and we can remove it. A pointer I can be retrieved using the AND operator applied directly at the time we invoke the function. The effect will be exactly the same. Okay, so we can remove the pointer and just replace it with a function x and then add this literal or this expression, and the result will be the same. All right, so now we are going to write a function which increases the value pointed by its parameter. We already know that the formal parameter has to be a pointer, so the complete function will look as follows. So we have void, and we have the function name incr, and its pointer is the value. We have the pointer value, and then we are going to increment it. Can you explain why we have to use the parenthesis using a surrounding asterisk value or the pointer value? What would happen if if we remove them. Now we are going to we are now we're ready to make use of our new function, and the main function would be int var equals 100, and this one we will declare the function incr, and then the variable here, and then printf variable is equals to var and then return 0. So the complete program is in the editor. So here's the complete program. We have declared the function incr, and we also the parameter has a pointer value, and we add the value inside the parenthesis a pointer, and then we are going to increment it. What do you think would be the output for this? All right, so if we're going to run this one, this will prompt var is equals to 101. So what do you think it it is the result? It is become the result because as you can see, we have the printf, we have var is equals to %d. So the var comes from the using the function we have declared before the printf. We have declared the function incr and its end variable, which the variable is from 101, and its expression from the function incr is increment to 1. So that's how we get one var is equals to 101. Okay, let's have the function parameters that are structures. Structures always pass by value, just like scalars. This means that the program in the editor will output the text 1a. That is, the fields of the str structure remain unchanged after the fun invocation. Alright, so how do we get 1 and a? So as you can see, the we have structure here, and the description is str int, its int is int char, and we have the variable char here, capital C, and we have two function named fun and main function. So if we are going to take a look at the fun, we have declared a structure int equals 2, and another variable for a structure s char is equals to b. So as you can see, we don't use this variable since the printf calls only the str int inside this function, which is equivalent to 1, and str char is equivalent to a. So that's how we get the value of 1 and a. However, we are allowed to pass a pointer to the structure as an actual parameter. Look at the example in the editor, which is only slightly different from the previous one. This function expects a pointer to the structure, not the structure itself. The pointer is of type struct str asterisk. Consequently, the function does not use the dot operator anymore. An arrow must be used instead, and the output screen will look as follows. So the expected output will be 2b. Alright, so this in the code in the editor, if we are going to run this, so we will get the expected output 2b. So how do we get 2b? So as you can see, we have the pointer here, and we use arrow. So this program in the code in the editor is in the same was in the same function in the previous slide, but the difference between them, it has the pointer, and we use arrow here. So the pointer points that we are going to use the int, the variable int that is equivalent to 2 here, and str char that is equivalent to b. So as you can see, before the printf function, we have declared a funx and str. So that is how we get the output to be. The function parameters that are one-dimensional arrays. Let us start with the following principle. Arrays are always passed as a pointer to the first element. That reminds us something, right? We have already seen the name of an array is interpreted as a pointer to its first element too. This principle is a simple consequence of a general rule. It means that any change made to a formal array's element value is immediately reflected to its actual array. This duality, which consists of different treatments of parameters that are or are not arrays, is often a problem for novice programmers. Now we will write a function whose task is to multiply each element of an array by 2. The array is declared as follows: int r is 5 equals 1, 2, 3, 4, 5. We assume that the formal parameter is simply a pointer. We are going to apply the indexing operator as if the pointer was the real array. Here's the complete program. Pay attention to how we deal with the ARRPTR parameter code in the editor. This program will output 2 lines of text coming from the context of the array before and after invoking the mul2 function. So the expected output is 1, 2, 3, 4, 5, and the second line would be 2, 4, 6, 8, 10. Note that the formal parameter is declared as a pointer. Void mul2 int. Then we have the pointer ARRPTR, while the actual parameter is the name of the array. Mul2, then array. So if we are going to run this code, this program in the editor, so this is the expected. This is the output. So how do we get that? All right. So as you can see, we have declared 2 functions here. The first function named is mul2, and the second function is name. So in the mul2 function, we have a parameter that is a pointer, and we name it as ARRPTR. And we have declared an int data type here, which is the name is I. And we also have the for loop, which is for the array, and it will be the initiator variable will be multiplied by 2 until uh, until to greater less than 5. So here in the main function, in the first function, we are going to print the array, and the initiator is I, which is equivalent to 1, 2, 3, 4, 5. So that is how we get this one. How about the second line? So after that, we will declare the new line here, and we also declare that the mul2, which is another function, and it is the parameter would be the array. So as you can see, the array is equals to this one, and we have another function here, or another conditional statement is which is the for loop. And before we print the array, we have the conditional statement, which is I is equals to 0 and I is less than 5, and we have the I increment. So if we are going to print this from using the mul2 function, as you can see, the I was multiplied by 2 until it becomes 2, 4, 6, 8, and 10. So that is how we get that output. Okay, so the function parameters that are one-dimensional arrays. Note that the part of the code used to print the content of the array is duplicated. This is a great opportunity to make a new function and to invoke it, instead of performing loops. The new function will receive the pointer as the actual parameter, but the formal parameter is declared differently than before. Look at the editor. The complete program is provided there. Pay attention to 2 important circumstances. First, note how clear the main function becomes when we get rid of the repetitive code. The name of the new function makes its purpose clear. This is what we call self-commenting. The word print affects the reader's imagination more strongly than any long-winded comment. We have used a slightly different technique for declaring the formal parameter. It suggests that we are going to deal with an array, not a regular pointer. So we have an array here, and it is A, and then the bracket. Although the declaration does not determine the size of the array. Why? Specifying the size of an array is unnecessary because the array already exists. It's already been declared somewhere else outside the function, and we only need a pointer to it. Note that the compiler's point of view, both methods of declaring formal parameters are equivalent to one-dimensional arrays. The function that sends the pointer to the array as a parameter cannot guess how many elements the array contains. An attempt to use the size of keyword operator comes to nothing. We will only get the size of pointer itself. The actual size is hidden from the function. There are two possibilities. The first possibility, the program only knows the size of the array, where we know that the array contains 5 elements. The second possibility, information about the array's size is passed using another method with the use of different parameter. There's also a third possibility. The information is encoded inside the variable just like a string. We are going to discuss this variant now. All right, so if we are going to run this program, you can see we will get the same result just like we have get in the previous slide. So that would be 1, 2, 3, 4, 5 in the first line, and the second line would be 2, 4, 6, 8, 10. So as you can see, we have 3 functions here. The first one is print, second one is mul2, and the third one would be the main. Okay, so in the main, as you can see, in the print function, you can see that we have the parameter int, and then we have an array, and we don't have the value of a here, since the declaration of the array is unnecessary because the array has already been exist and it's already been declared someone else or here in the main. So here on the array, we have declared the value of the array, and that would be 1, 2, 3, 4, 5. So the first thing that we will do is to take a look at the main. So here, the main function declare that, and it calls the print function, and it has an array variable, which print function stands for, or the function of that would be to print the percent %d, which is equivalent to the array, and that array is equivalent to 1, 2, 3, 4, 5. So that is how we get that. Okay, so how about the second line, mul2 and then array? So the function of this is just only the declaration on how to multiply the array by 2. So that is how we do that. We declare the I in the for loop. We have an, and its formula on how to multiply by 2 each elements in the array. And how to print that is also declared another print function here. And as you can see, we have we can only get the result of 2, 4, 6, 8 if we first write or declare the mul2 function. So that is how we get that result. Let's have the function parameters that are strings. A string is just a special type of array. We know that first, it's an array type of char. Second, the array content must end with the empty character that is null. We will try to write our own implementation of the strlen function. We know that its prototype looks more or less as follows. Int strlen, then we have the parameter char, and then the pointer str. The function finds how many characters are contained by the string pointed to by str parameter. To avoid confusion and to distinguish our function from the original one, we will name our function mystrlen. The use of my prefix is a common and popular practice used by developers whenever they come to write their own version of well-known and widely used function. We will also make the following assumption. First step, we require a counter with the initial value of 0. Here, it's the initial value of 0. Second step, we check the character pointer by str, and if it is null, we will leave the function and returning the current counter value of the result. So by checking it, the value of str pointer, we can use the while conditional statement. Step 3, otherwise we will increment the counter and move the str pointer to the next character inside the string. So if the expression meets the conditional statement, we are going to increment the counter. Okay. So in the last and fourth step, we will return in the step 2. Note the steps 2 through 4 from a loop. The conditional is checked at the beginning of the loops, so we will use the while loop for our algorithm. So remember that the while loop will only execute our program if the condition if it is um, passed or declared as true regarding to its parameter or its conditional statement. In the editor, you can see the first, maybe a little awkward approach to solving a problem. So that is how we use the strl, and we use our function named mystrlen, and we have also used inside its parameter an str pointer. Okay, so that is how we do that, the function parameter that are strings. Okay, let's have making improvements. Let us make some improvements. Some will be obvious, some will be tricky, but all of them are worth considering. So let's have improvement number 1. So the original code is while, and then its conditional statement would be the pointer str and is not equals to \0 or null. Knowing the assumptions that C language makes regarding true or false values, we can shorten the values that we can shorten the condition and encode it in the following way. So we can have while and then str pointer, and then our statement here, or the code. So as you can see in the editor, we use this the code the following way, and we already removed the not equal to null. We have about improvement number 2. If we can take into account the priorities of asterisk and plus plus operators, we will come to the conclusion that the condition in the body of the while loop. So here's another improvement, or here's another change, or how to simplify our code. So we can have the while loop, and under it will be the counter plus plus, or the increment, and another the str, which is the pointer, and another increment for the itself. Maybe encoded in a much more comprehensive form. Look at the editor. Look at the code in the editor. So here we have used a mystrlen, and this is also a function. This is also a function as a character. Okay, so we have char and then pointer str, and we have also declared a counter variable that is equals to 0, and then a while, then str. Okay, so we will return the variable counter. So that is the improvement number 2. Alright, so let's have another improvement, which is improvement number 3. Try to see the following interesting dependency. The first one is initialization, just like counter is equals to 0, and checking is str pointer plus plus, and modifying counter, which is the increment to the variable. Does it remind you of anything? This is exactly how to describe the for loop, right? So let us use it in our program, check the code in the editor. So note that the loop's body contains no instruction. It's empty and it's encoded as one semicolon. The semicolon itself, without any coupled instruction, is called in the empty instruction, which doesn't have any effect. So as you can see in the code in the editor, this remind us the for loop, and as you can see inside a for loop, we will have the semicolon, and this is called an empty instruction. So that is the improvement number 3, using the for loop. Okay, so let's have another slide. Okay, how about the improvement number 4? Look at the editor, the code in the editor. Note that there is the redundancy. We increment 2 dependent values, the counter and the pointer. We will try to simplify our algorithm and increase one variable. The first option will increment the counter only. So here we have increment the counter, and oh, this is wrong. This would be this. Okay. So this would be the improvement number 4 for string as function parameters. How about improvement number 5? Now we will increment the pointer and remove the counter from the code completely. We will need the second pointer though, which will be responsible for pointing to the beginning of the string. So the second pointer will be this one, the begin pointer, and the first pointer will be the str pointer. So in this one, the second pointer will be the responsible to point the beginning of the string. Okay. So that would be the improvement number 5. Now we are going to implement our version 2 of the strcpy function. The original function has the following prototype. So we have the prototype of the syntax char, then strcpy pointer, and then we have the parameter which is enclosed by parentheses, and that would be char destination pointer, and we have comma, another character which is source pointer. So the function copies all the characters from the string pointed to by source into the string pointed to by a destination, and returns the destination pointer as the result. So we can describe the algorithm in this way. So first, we have to store the destination pointer in the res variable. This is the res variable, and we already stored the destination of the pointer. Second, we copy the one character from the char pointed to by the source to the char pointed to by the destination. So this would be the source and this would be the destination. We already copied the character to the char point, and take note that this is infinite loop, finite or infinite loop. And then third, we are going to check the char was the empty char. If yes, exit the function and return the rest variable as the function result. Otherwise, increase both source and destination pointer. So in this and the third step, we use the if else. The if statement. So if the status of the code would be inside the conditional statement of if, uh, it will exit the function and return the rest variable as the function result using the break keyword. And then, or if else or otherwise, this will increase both source, destination, and source pointers. Okay, so and the step 4 will return to step 2, which is to copy the character from the char pointed of the source, this one. Okay, it will return it. Okay, so how about, again, we start off the simplest and maybe a rather naive solution. Look at the code in the editor. So as you can see, we have described it one by one in the following step of the algorithm. The first modification is based on an interesting property of the equal operator. The assignment operator sets its left argument with the value of the right argument, but also return the value which has been assigned already. The value of 2 plus 2 expression is 4, and in the same way, the value of the expression I is equals to 2 times 3 is equals to 6. This feature of the equal operator is often used by expressions similar to the following one. I is equals to j equals to k equals to 0, which should be interpreted as follows. So I is equals to parenthesis j is equals to k is equals to 0, and which will result the substitution of 0 into the variables k, j, and I in order, which is obviously more elegant than k is equals to 0, j is equals to 0, I is equals to 0. And in addition, the condition if then source pointer is equals to null can be simplified as if then not equals to source pointer, since we already use a null. Okay, so we can shorten our function now. Look at the code in the editor. The code, however, requires a few more words of the comment. The heart of the idea is the if condition encoded as. Here is the if condition. It's not equals to destination pointer is equals to, this is how we read this one. Destination pointer is equals to source pointer is not equal to not destination pointer is equals to source pointer. The expression will be calculated as follows. First, the first goes to the assignment destination pointer is equals to source pointer. The value assigned to destination is negated, so this is commutative. If it is a regular character, the result of the negation will be 0, so the condition is considered as false. If it's null character, the result will be equals to 1, and the condition becomes true. Okay, so let us try to implement it in a more comprehensive way. Check out the code in the editor. Here's a small code fragment to test it. So we have the char str array. So this is an array named str1 and equals to not so. We have also an array, character array, that is equals to best test. And we have my strcpy, that is str1 and str2. Okay, so let's have this. Okay, so as you can see in the program, the editor, in the code in the editor, you can see the for loop, which is we have used rest is equals to destination, and also another parenthesis, which is destination pointer is equals to source pointer. So we have discussed this improvements in the previous slide. So inside of for loop, we can see that we will increment each of pointer, which is destination and source. And after this for loop, otherwise it will return to rest. Okay. All right. As an alternative, more compact way of implementing it, check out the code in the editor. We would even go as far as to say that there's no way of writing it in a more condensed way. Are you willing to accept this challenge? Here's a small code fragment to test it. So here we also declared the previous, and here in the previous slide. So to make it simplified, instead of writing those code in the previous editor, we can delete the part of just with the second. We can delete this increment, and just after the for loop, we can return it to rest. As you can see, we don't have any increment after the for loop, but we have insert the increment itself to the pointer. Okay, so we already added here to avoid duplication. And this is a more simplified and more easy. This is only an alternative way, but it will also result. It will also give us the same result. So how about this one? Now we had like to show you our own version of strcat, or concatenation function. Note that the prototype of the function is char, strcat pointer, and then char destination pointer, and also another character which is a source pointer. So second one, the result of the function is the destination pointer. The third one, the function appends a copy of the string pointed to by the source at the end of the string pointed to by the destination. We hope this code intrigues you and encourages you to solve the mystery by yourself. Okay, so as you can see in the prototype function, we have the char str here. This is the prototype of the function. And inside the block, we have declared the rest pointer, and as a result, the function of the destination pointer. So here uh, we have declared two for loop. That is the result of the function destination pointer. So here we also declared the incrementation of the destination pointer. And this function block also appends to the copy of the string pointed to the source of the end of the pointer to the destination. So here's how we do that using this for loop. Okay. All right, guys. So this time we will post this fifth session of Module 3, Part 1. And this concludes the fifth session, Part 1 of Diverse Node Mobility Front-End Development Program. See you on the fifth session, Part 2 of this course. So have a good day. Thank you guys.